Okay, in this video, we'll be going over reaction mechanisms and some terms like elementary steps, intermediates, how to write a rate law from looking at a mechanism. And we'll also be going over how to write a rate law, which is a little bit different if the mechanism, the first step is slow versus when the first step is fast. So you do it a little bit differently. So let's go over some terms and we'll look at some examples, and then I have a couple questions at the end for you guys to try. So first of all, reactions. This is stuff we've covered already. They involve many steps, not just the overall reaction. So let's say, let me throw an example up here just so I have something to refer to when I'm going over these terms. So if you have like a reaction, let's say you have 2p, I'll be working with this hypothetical reaction later. So 2p plus q makes 2r plus s. And this is the overall reaction. So we have an overall reaction. This is something you've been seeing all year long. And let's say like at during this arrow, we're like, what exactly is going on during that arrow? So there's a proposed sequence of things that happen that need to happen for these to create these, and we call these mechanisms. So it's kind of like zooming in on this reaction arrow. What is going on during that reaction arrow? That's really like the fundamental thing about this whole chapter. So things are colliding, reactants are colliding, they're breaking bonds, and new bonds are forming. So this is kind of like the on an energy profile, this is like the things that are happening here at this hump, and they're things that are like really hard to study and figure out and identify what they are. They're there's things that they get created and then they get consumed in during the mechanism. So if we shed some light on this arrow, we can propose what's going on during this arrow. So there's a series of things that could be happening. So this is a proposed mechanism. P plus P makes R plus, or sorry, makes something called T. And right away we see something kind of strange. T is not showing up in the reaction. So this is actually called what's called an intermediate. So that's the first step. Let's say this happens in actually a series of steps. Step two, we have Q will consume T and make R plus U. And then you'll see again that U is not part of the reaction. So U actually gets consumed in the next step, which we'll call step three, makes R plus S. So you'll see that T is something that actually is not part of the reaction, but it's something that happens in during this arrow. It's something that exists up here. So we would assume, which is correct, that T is something that's unstable and it exists for not very long, and it before it gets consumed. So T is what we call an intermediate. So let's go over some more terms, and we'll be working with stuff like this. So what I just wrote, these things that are happening, these sequence of things that are happening, are called elementary steps. So it's not the overall reaction. These are the elementary steps. The overall speed of the overall reaction when these make these is determined by the slowest of these three steps, the elementary steps. So a lot of textbooks use this analogy where if you go home, let's say there's a series of 6 steps that it takes to go home. So you have to make like a left turn and then another left turn, and then you make a right turn, and then you go straight for a while, and then you make another right turn, and then you get home. Let's say every time you go home, this right turn just takes forever. You're at like a school crosswalk or something, and it just takes forever. So this is fast, fast, and this one is slow. We would say that the overall rate is determined by the slowest of those steps. So just like in a chemical reaction, we have these 3 steps. One of these might be the slowest one, and the others are much faster. So that's called the rate determining step, the one that goes the slowest. An acceptable mechanism proposal, and we don't know which ones are correct until you can confirm it with an experiment. So this is um, so this is the proposal here, and it may or may not be acceptable. It has to follow two requirements. So the sum of all the elementary steps need to result in the overall reaction. So if you remember Hess's law from, I think it was chapter 5, the thermochem chapter, if you if something gets created and then it gets consumed, that's not part of the overall. And as we see, T is not part of this overall, so it needs to be getting consumed in these elementary steps, and it is right here. So T gets consumed. U also is not part of this, so R also gets consumed. And what we have is 2p plus q. Remember, t goes away and u goes away, and it creates 2r plus s. So this one actually works. These three elementary steps, they would result in this overall reaction. So first requirement is fulfilled. And the rate determining step the slow step has to agree. So this slow step right here, what this actually means is the slow step, it has to agree with the overall um, rate law that is determined by the method of initial rates or a test plot method. So let's say the first step is the slow step here, and this step is fast, and this step is also fast. Okay, the what this is saying is when the first step is slow, the coefficients of this step must match the exponents of the rate law. I think this is better explained with some examples later, so we're going to get to those in a second. When the first step is fast, it's done a little bit differently, and the overall rate law, which cancels out intermediates, should be derived. And again, these two bullet points are better shown with a couple examples. So let's go get to those examples. So this is kind of covering some of the terms and all that. So intermediates and catalysts and a mechanism. So here's an example reaction. It's actually this is actually showing the destruction of ozone by nitrogen monoxide. So ozone in the upper atmosphere is a protective layer. It absorbs UV light. If you remember the Lewis structure for ozone, um, it actually um, it actually does resonance, so it has delocalized electrons which absorb UV light. In the lower atmosphere, it's bad because our lungs mistake it for oxygen, O2, and then it causes like bronchitis, inflammation in the lungs, stuff like that. But in the upper atmosphere, it's necessary to block harmful UV light. It absorbs it and dissipates the energy. So anyway, this is a reaction, and ozone will on its own decompose into O2. So it says which species is an intermediate and which is a catalyst. So if we look at this, we see that NO is in the reactant, and it also appears again. It gets consumed in the first step, and in the second step, it actually gets regenerated. So this is not part of the overall, but it actually got regenerated. So we call that a catalyst. So catalysts appear at the beginning and are regenerated as products. And also note that since they actually cancel out, they do not appear in the overall balanced reaction. They may, however, they may appear in the rate law. So they actually their concentration may impact the rate. It may or may not, the catalyst that you add. Okay, so this reaction is actually showing, it's also showing an intermediate. So if you notice, NO2 gets produced here in the first step, and then it gets consumed in the next step. So NO2 is an intermediate, and the difference again is NO got regenerated. It appears at the end of the reaction. So the one that I have labeled in blue is an intermediate, and these are, so look for these being produced in one of the first, one of the initial one or two steps, and then look for it getting consumed right away in the next step. That's what's happening here. So they get created as products in one elementary step, and then consumed in a later step. Um, we could go ahead and write the overall reaction here. So um, the overall balanced reaction is O3. Uh, let's see, reacts with O to make 2 moles of O2 is what I have. Okay, so let's go to, so that just covers those two terms, like how to identify a catalyst or an intermediate. I wanted to, let me go back to the previous slide, and I wanted to cover some of these terms, like this part right here on the next question. So let's take a look at how to satisfy the requirements for it to be an acceptable mechanism. So here's the reaction. Okay, and this is the observed rate law. This is the observed rate law by method of initial rate. So this is the accepted rate law here. And notice that this does not match, the exponents here do not match the overall exponents. What these must match, so these must match the exponents, or sorry, these exponents in the rate law need to match the coefficients of the rate determining step, or the slow step in the mechanism. Okay, and this is when the first step is slow. I should say that as part of the, it's done a little bit differently when the first step is fast, and I'll show you two examples of that. So later. So this is when the rate determining step, we'll call it the RDS, is the first step. Okay, so which of the following is an acceptable mechanism? Mechanism 1. So let's take a look at this. Let's just put them all up here, and we'll take a look and see which one works and which ones don't and why. So mechanism 1 is proposing that this reaction, it's proposing that this reaction occurs in one single step here. It's proposing that it occurs just as written here. So uh, the first thing that's true is this actually equals the overall, so that works. So this equals the overall reaction. But what doesn't work is the coefficients do not match the rate law exponents for the rate determining step. So if this is occurring in just one step, it must also be the rate determining step. And if you look at this 2, it matches this 2, but this 2 doesn't match this 1 right here. So this one does not work. This proposed mechanism doesn't work. So let's look at this one. Let's first check to see if these equal. Do they equal the balanced overall? So we're gonna kind of use like Hess's law here, and this nitrogen cancels with this nitrogen, so that must be an intermediate. This oxygen cancels here, And then we see that we have two H2s and we have two NOs. So that's this and these. So I accounted for those with the coefficients I wrote. And then the H2O and H2O, so it makes two H2Os plus an N2. And this works. So this does equal the balanced overall. It equals this reaction right here. So that works. Now let's see the slow step. Let's check the slow step. So it has to follow these two check marks. Do the coefficients match the exponents in the rate law? So do these match? So let's see that it has one H, so that matches. But in my slow step, I only have one NO, and in my rate law, it's accepted that there's two of them. So and what? So let me back up. The book actually goes over some terms called molecularity. This rate law is suggesting that two of these in the slow step, two of these need to collide with one of these for this mechanism to for this to proceed, for this reaction to proceed. Um, so what this is proposing is that only one of these and one of these are colliding. So this doesn't work. This mechanism doesn't work because the coefficients of the slow step don't match. And this is called a you could see more of this. They have like a chart in the book. But this is called a termolecular because it requires in the rate law it's showing three molecules are colliding at the at the height of the energy profile. So uh, let's see, does this one balance out? So the N2O that cancels, and as you see, N2O doesn't appear here, so that's the intermediate, and it should cancel. We have two H2s plus two NOs, and it makes two waters and one N2. So this actually works. So the first thing we're looking for checks out, and then does the rate determining step, the first one, does that match the coefficients? So we have one H and one H, and then two NOs and two NOs. So this works also. So the coefficients equal the exponents of the rate law, and it equals the overall. So all the intermediates cancel correctly to equal the overall. So we say this is an acceptable mechanism, and it still has to be tested by experiment and to make sure that this is how it works. Okay, so that's an acceptable mechanism. Let's move on to another example. And this one is really the same question, but it's looked at, kind of a different angle here. So here's a proposed mechanism for a reaction. So we have this creating these two things. And as we notice, this is getting created and then it gets consumed right away. So this is this one here is an intermediate. So this gets consumed here. And I think we have another intermediate in this reaction. So yeah, this one right here gets created, and then it gets consumed in the next step. So we're going to have two intermediates. So it says write the rate law expected from this mechanism. So we just look at the slow step, and notice in my title I put this is only works when the first step is slow. So you have to notice that. So you have to check all the elementary steps, and you go, oh, this is an easy one because the first step is slow. And I could just, when I want to write the rate law, it just equals the coefficients of the reactant in the slowest step. And again, it just deserves repeating. This only works when the first step is slow. I have another example in the next slide where the first step is fast, and it's done a lot differently. So we write the K. So each of these will have like a K value. This is K1. We'll call this K2, and we'll call this K3. So each elementary step, they actually have like their own little mini rate laws. And the only one that's the overall rate law is the slow step. So we'll write K times the concentration of C4H9Br. And we check the coefficient, and it's a 1 right here, so it's first order. So that's the rate law expected for this mechanism. Easy, right? So if the first step is slow. Okay, so it says what's the overall balance equation for the reaction? So I cancel out the intermediates, and I'll write the overall. So I already kind of like what I wrote in purple here and here, those cancel and the blue one cancels. All right, so the leftovers is what I'm going to write. So this plus two H2Os to make Br minus plus C4H9OH plus H3O. So there's my overall reaction. And then now this asks what are the intermediates. So those are the things I canceled out. So C4H9 plus, and you have another intermediate. Notice there's no catalyst shown here. There was nothing that was created and then regenerated as a product. There's nothing like that here. Okay, so and the thing I wrote circled in blue, C4H9OH2 plus 1. Those are the two intermediates. So if we here's kind of like a thought question I included. Question 4. It says, what does the proposed rate law mean for the effect of H2O on the overall rate of the reaction? So as you see, the overall reaction includes H2O. So if you notice, H2O is not part of the rate law. So what must that mean for H2O? So if I can make this like 1 million molar, does that have an effect on the overall rate? No, because it's not appearing here. So what does that mean? What does that mean for H2O? What order is it for H2O? It must mean that H2O is 0 order. So H2O, so whatever the concentration of H2O is, if you take it to the 0 power, it would equal 1, and it would not affect the rate. So if I include H2O here and write a 0 here, it essentially cancels out the H2O. It just turns it to 1 no matter what it is. So it must mean that H2O is 0 order. Okay, so let's look and see how this is done if the first step is fast. So you have to notice that. You have to kind of go, like, you look at the proposed mechanism. So here's a reaction. This is the overall. And you look at the proposed elementary steps in the mechanism. And you have to look at these when it says fast and slow or slow and fast or whatever. And right here, you have to go a light bulb. This is a light bulb. Pop. Uh-oh, the first step is fast. This one's going to be a little more involved, writing the rate law. We can't just go like this. The rate law, the overall rate is determined. This is the rate determining step here. And I'll tell you the problem with this. This is the rate determining step. So we'll write that the rate is equal to, we have to add some little, I'm going to add little k's here. This is k, and this is k negative 1. I'll get to that in a second. This is K2 for the second step. So let me label the steps. This is the first, second, and third step. And we have a little rate constant for the third step. So all of these reactions, and you'll notice like what's going on with those double arrows. So I'll explain that in a second. So the rate of this reaction is given by this. So we're going to write K2 times the concentration of Q times the concentration of T. And notice these are the coefficients are 1, so that's a 1 and that's a 1. Okay, so here's the problem. This is the rate law. This is the rate law for the reaction is this. But the problem with this is we just express the overall rate in terms of an intermediate. So T gets consumed here. And this is not desirable. It's not desirable to write the rate law in terms of one of the intermediates because we can't control T. We don't know what T is. T, remember T, so our overall reaction is this, right? So T essentially doesn't even exist. It's some weird unstable thing that we can't control. So what we want to do is we want to be able to write this, the overall rate, in terms of P and Q. So when the first step is fast, you need to write the overall rate law in terms of the reactants. And in this case, that would be P and Q. So we need to derive an expression that gets rid of T. And this can be done if you use a couple of assumptions. So if the second step is happening slow and the first step is happening fast, then T just kind of sits there for a while. So T gets created And since this step is slow, T just sort of like sits there. If you remember our analogy to like driving home, so let's say the first step in going home is going left, and then you make another left, then you go straight for a while, and then you make a right, and then another right. And let's say this right turn is a slow step right here. So let's say like you get stuck right here, and you go, you know what? Forget this. Let's just do this another day. Let's just go back home. So, or let's say like you're trying to go to the store, okay, and then you get like stuck right here in some traffic jam. There's an accident or something. And you know what? This is not worth it. I'm not even gonna go forward anymore. I'm just gonna go back home. Forget this. Okay, that's what T is likely to do here. In fact, that's the assumption that we have to make. Instead of going forward in this reaction, T will just kind of sit here. Instead of going forward in reaction number 2, it actually goes backwards and makes P again. So if this is happening fast and this is happening fast, just as fast, we can say the rate of the forward reaction is equal to the rate of the reverse reaction. So let's write a couple of rates to express that. So we'll write that going forward in that reaction, we'll write that the rate forward equals K, and this should be K1. I should write K1 here. K1 times the concentration of P squared. So I'm looking at the reaction going this way, and I'm gonna say and I'm gonna write another rate law for the reverse reaction. Reverse equals K minus 1, and this time I'm looking at this reaction going right to left. So in this case, the reverse, this is my reactant, is T. So I'm going to write T, the concentration of T. Okay, so remember that this is happening fast and this is happening ultra fast. So we're going to say, since it's the same reaction and we have a forward and reverse, we're going to say that these rates are actually equal to each other. So we're going to say that this, let me switch back to black here for a second. So we're going to say this is actually equal to this. So we're going to write K1 P squared equals K negative 1 times T, the concentration of T. And notice that the whole reason we're doing this is to do this. We're trying to eliminate our overall rate law in terms of T. So using substitution, we're going to solve this for T, and we're going to divide both sides by K minus 1, K minus 1. This cancels, and then we have an expression for T now equals K1 over K minus 1 times P squared. Okay, and now we're going to take this. So we're going to take this guy, and then we're going to plug it in for T and leave everything else there and clean it up a little bit. So we're going to take this and then rewrite this. The overall rate equals K2. So we're going to leave everything there except for the substitution part. So we're going to write K1 over K minus 1 times P squared, and voila, we actually have an expression that puts it in terms of the two reactants. We have P and Q in our overall rate law. So let's clean this up a little bit, and we'll bundle up all the rate constants, and we'll go K2 times K1 over K minus 1 equals a brand new rate constant. Since they're all constants, we can just make up a new constant and say that K overall is equal to these little pseudo rate constants, these divided by this one. Okay, and then we'll write the overall rate for this as K overall times the concentration of Q times the concentration of P squared. And this is the rate law. And that's how you do it when the first step is fast. So it's a lot different than so it's not simply just writing it the rate law in terms of these coefficients because of the whole intermediate problem, and we don't even know what the heck the intermediate is. So that's why we have to do that. All right. So now some questions for you guys to try. This is the this is the your turn. It's kind of similar to that how I was identifying what were intermediates and is there a catalyst here? I'm not sure. Yeah, yeah, maybe. It's for you guys to figure out. So it's identify any intermediates or catalysts in this reaction. So this is kind of like the beginner kind of problem. Then your turn two is I have kind of a similar question here as the previous one, but it's a slightly different angle to look at it. And you're again identifying intermediates and the catalyst. And this one, notice I did when the first step is slow. So you're going to write the rate law for when the first step is slow. So that's a lot more simplified than when the first step is fast. And of course, so you know what that means. In your turn number three, the third one, so I'll give you a second to pause it if you want to write this question down. So if this one I have the first step is slow, you probably guessed correctly that in your turn three I have a reaction where the first step is fast. So it says derive the overall rate law, and I put note. Remember, it's not desirable to write rate laws showing intermediates, and I put show all your math work in your derivation. Okay, that is the end of our tutorial.